Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll summarize the performance results from using OpenMP, Open Multiprocessing, for parallel computing on the Betzy and Fram Linux clusters. We will compare the wall and CPU times across various methods previously demonstrated in our videos. In our Fortran program designed for matrix multiplication, we utilize the parallel do directives on the loop responsible for the multiplication process. We compiled the program with the Intel Fortran compiler, which substitutes this loop with an optimized routine provided by Intel. Consequently, the OpenMP directives are implemented within this optimized routine. On the Fram Linux cluster, we conducted tests without applying any OpenMP directives to the initialization process. As a result, the initialization loop did not execute in parallel. We will refer to these tests as one loop. The test that applied OpenMP directives to the initialization loop will be labeled with toLoop, allowing both loops to execute in parallel, thus parallelizing all parts of the program. On the Fram Linux cluster, tests were conducted both with and without inter-procedural optimizations. Those with optimizations will be labeled with IPO. Additionally, tests were performed to evaluate OpenMP affinity using either close or spread binding, and these will be referred to as close and spread. The displayed figure represents the wall time for all tests on the Fram Linux cluster. Be aware that the wall time axis utilizes a logarithmic scale to facilitate easier reading of the data. The one-loop test showed the longest wall time with 16 and 32 threads, indicating the least efficient performance. In contrast, the two-loop test, which executes the entire program in parallel, demonstrated better performance. The inter-procedural optimizations, IPO, did not significantly affect performance during the tests. Both the close and spread tests under OpenMP affinity settings performed similarly and achieved the best results. The next figure displays the CPU time for all tests conducted on the Fram Linux cluster. Please note that a logarithmic scale is used on the CPU time axis to enhance readability. This figure provides a more detailed comparison of test performances than the wall time figure. It reveals that OpenMP affinity with spread binding outperforms close binding in tests using 16 or fewer threads. This figure illustrates the wall time for all tests conducted on the Betzy Linux cluster. Note that the wall time axis is presented on a logarithmic scale to enhance the clarity of the data. All tests on Betzy included inter-procedural optimizations, IPO, which were crucial for achieving good performance. The figure indicates that OpenMP affinity with spread binding delivers the best performance for configurations using 32 or fewer threads. In contrast, close binding yields the best results when utilizing 64 or more threads. The CPU time figure offers a detailed view of performance, showing that OpenMP affinity performs equally well with 8 or fewer threads. Spread binding achieves the best performance with 16 or 32 threads, while close binding is most effective with 64 or more threads. Note that we are employing a logarithmic scale on the CPU time axis to improve readability. Why does performance decrease when using many threads? Several factors can contribute to this issue, but a common bottleneck is that multiple threads access the same data elements. Essentially, when using parallel computing with threads, multi-threading, the threads share the same memory, which can lead to performance issues. In our Fortran program, the matrix C is an example of such a data element, represented by the blue square in the figure. The red arrows indicate threads that are reading from or writing to matrix C. If many threads are doing this simultaneously, it can lead to a bottleneck. When threads try to write to the same memory location, there must be some mechanism to ensure that the data remains consistent and that updates are not lost. This typically involves locking mechanisms, which can significantly slow down execution as threads wait for access to the shared data. You might wonder why we use Linux clusters with thousands of CPU cores if achieving speed up with more than 16 or 32 threads is difficult. To effectively use a large number of CPU cores, we must adopt a more advanced level of parallel computing called multitasking. For instance, we could split matrix C into two smaller matrices, CR, as illustrated in the figure. This division reduces the number of threads accessing each smaller matrix CR, thus easing the bottleneck related to data access. However, dividing matrix C into two matrices CR necessitates some data exchange or communication between them, making communication a vital component of multitasking. While it's possible to perform parallel computing using pure multitasking with just one thread per task, often a hybrid approach, using more than one thread per task, yields better performance. In our upcoming videos, we'll explore advanced parallel computing techniques, including multitasking and hybrid models. But first, our next video, we will discuss the benefits of scripting versus typing. I am looking forward to the next video, wishing you all happy computing in the meantime.